We start our session with the topic error detecting and correcting codes. So this is one of the BCD code which comes under your error detection and correction codes. So basically Hamming code is the best example of error detection and correction codes. Now whenever we are going to transmit your data, so or storing your data, so there was a very high chances that data may be corrupted. So since we have only the possible values are ones and zero, so there was a high chance that can change the bits. So or the bits may be flipped from 1 to 0 or 0 to 1. So error correction codes can detect your error as well as we can also correct the errors by finding where the error is occurred. So this can be done by using your parity bits. Like in your error detecting codes, we are going to use your single parity bit in error detection code, whereas in error Hamming code, we are going to use a block of parity bits. So by just dividing your data into multiple blocks, for each blocks, let me assign your parity bits, and based on your parity checking system, we are going to find your where the error is occurred. So now this is only used for to detect your single bit error, as well as it can also detect the presence of your 2-bit error in a data block. So your Hamming code is uses the block parity scheme mechanism, and the data is divided into blocks. For each block we are assigning one of the parity bit. So it has to follow a relation which is 2 power p must be greater than or equal to d plus p plus 1, where p denotes the number of parity bits to be added to transfer your the d number of data bits. So d denotes your number of data bits. For example, now if I wanted to transfer a 7 data bits, minimum number of parity bits required that I have to determine by using your trial and error method. So by replacing your p with started with a 1. So if I start with a 1, so 2 power 1 become 2, so it may not satisfy that relation of 2 power p is greater than or equal to d plus p plus 1. Now let me replace p equal to 4, then it become 2 power 4 becomes 16. 16 is greater than or equal to 7 plus 4 plus 1, which is 12. So it satisfied that relation with p value of 4. So hence in order to transfer your 7 data bits, the minimum parity bits required is 4. So if I add those minimum parity bits of 4 with my data bits, my Hamming code could have your total number of bits are 11 bits. 7 plus 4 become 11 bits. Now the second example that I take to generate a 7-bit Hamming code. So in order to transfer your 4 data bits, so first we have to determine how many minimum parity bits that are to be used and how many blocks of data we have to categorize. Now, so to transfer your 4 data bits, so the minimum number of parity bits are 3. So now let me verify the relation here. 2 cube become 8. So 8 is equal to exactly 4 plus 3 plus 1. So it is exactly equal to 8. So hence to transfer your 4 data bits, we require 3 parity bits. Now along with this parity bits with the data bits, if I am adding those two, 4 plus 3, now the Hamming code contain the 7 data bits. Next thing is we have to allocate where I need to substitute your data bits and how to substitute your the positions of your parity. So we have to determine where I need to substitute your parity bits. So now parity bits can follow the power of 2. So power of 2 is nothing but 2 power 0, 2 power 1, 2 square. So 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4. So next the remaining positions are added with the data bits. Now here, so now verify your parity bit positions. So here it is 0 0 1, parity 1, and parity 2 is 0 1 0, parity 4 is 1 0 0. When I compare with the remaining all the data bits, only these three could have a single 1 in its binary representation. So 0 0 1 is having one, only 1 in binary representation. Here also 0 1 0, only 1 we have, whereas parity 4 is 1 0 0, it is also having only 1. So hence it follows your parity positions follows your power of 2. So we placed P1 at 2 power 0, 2 power 1, placed your parity bit 2, and parity bit 3 which denoted as here it is P4, but the position is fourth position. The remaining position we added your data bits. Most significant data bit is placed on your left end, and the least significant digit is placed on right side. So now, so D1 is your most significant digit of a given number, D2 is your next most digit, second most digit, this is your third most digit, and your last digit is least significant digit is placed on your data 3. So with this, so if I'm adding these 3 parity bits along with these 4 parity bits, I could have the code can contain the total number of bits r is equal to 7. Hence, the block length become 7 here. We call this as a 7-bit Hamming code. Now, so we have to determine, so after determining their position, we have to determine their values. So in order to find their values, so first we have to divide the block of data into groups. As here 3 parity bits, so block of data is divided into 3 blocks. So where block 1 checks the bit positions of 1, 3, 5, 7. The block 2 will check the positions of 2, 3, 6, 7. Block 3 can check the positions of 4, 5, 6, 7. So based on your 3, 5, 7 parity 1, and based on scheme of your parity, whether you are preferring a odd parity scheme or even parity scheme, in Hamming code we are going to prefer your even parity scheme. So based on the positions of 3, 5, 7, so your parity 1 value is decided whether it is a logical 1 or it is a logical 0. If 3, 5, 7 contain the even number of ones, then P1 becomes 0, parity bit 1 becomes 0, because already our data bits are containing the even number of ones, hence parity 1 becomes 0. So now parity 2 value is decided based on the data bits of 3, 6, 7. So now if 3, 6, 7, if it doesn't contain your even number of ones, then P2 is 1. If it contains the even number of ones, then P2 value becomes 0. So next, P4, the last bit of your parity, is determined based on the positions of data bits 5, 6, 7. So now based on the positions of 5, 6, 7, if they are even, then it will be logical 0. If they are odd, the received data bits are 5 on your 5, 6, 7 is odd, then the parity bit 4 is 1. So we can set your parity bit whether it is equal to 1 if all the values of its data bits are odd. So next we can set that value of parity if it is set the parity bit it is 0 if total number of received data bits are even. Next, how to encode your 7-bit Hamming code. Now with the example we can explain this. So I have taken a decimal number which is 12 and its binary equivalent is 110. Now our data bits are 4 data bits. I have here is 1100. Most significant bit is 1. So now that is placed at data 7 and this 1 is placed at data 6 and 0 is placed at data 5 and 0 is placed at data 3. Now we need to determine your parity 1, parity 2, parity 4. We have denoted that with a unknown symbol which is X. So these values are unknown until we find your or check your data bits whether I received a even number of ones on data blocks each data block or not. So now to find your parity 1, so we are checking the positions of 1, 3, 5, 7. 1 is itself it is a parity, so where the value is dependent on 3, 5, 7. So 3 received with 0, 5 is received with a 0, 7 is having a data bit of 1. So now your number of ones here it is 1. So hence the parity not to make a even parity. So parity 1 value must be 1. Next, in order to find your parity 2, so we were checking the data bits at your transmitter, received data bits at your data bits which is 12 is 3, 6, 7. So now 3 is 0, 6 is 1 and 7 is 1. So you can add it or you can count it. Okay, so if I am adding 1 plus 1 plus 0, I was obtaining the value of 2. So now the 2 value is a even number. So hence P2 value become 0. or you just simply count it. Number of ones received is data 7 is 1, data 6 is 1, and data here 3 is 0. So now hence here number of ones received is even. So hence parity 2 is 0. Next, parity 4 is dependent on 4, 5, 6, 7. So this parity 4 depends on the data bits of 5, 6, 7. So 5, 6, 7 contain the even number of ones. Hence parity 4 is 0. Now upon determining your P1, P2, P4, P1 value with 1, P2 value with 0, P4 value with 0. Now encoded 7-bit Hamming code after replacing parity 1 with 1, parity 2 with 0, parity 4 with 0. My 7-bit Hamming code, which is used for checking your errors or to detect your errors. So which is 110001. So this is at the transmitter end we are going to generate, and through the channel we were transferring your given data bits. So then upon receiving at your receiver end, your receiver can check for the errors by recalculating their parity bits. For example, if I receive the data bit of 7 bits, 7-bit Hamming code, which is 1501. Now we need to go for the recalculating your parity bits, so which are denoted as correction bits. C1 checks the positions of 1357, C2 checks the positions of 2367, C3 checks the positions of 4567. So C1 is checking the positions of received data bits of parity 1, data 3, data 5 and data 7. So 1 exclusive OR of 0, 1 exclusive OR of 0 and 0 exclusive OR of 0 and 0 exclusive OR of 1. So received data bit on parity 1 is 1. So 3 is 0 and 5 is 0, 7 is 1. So now 1 exclusive OR of 0 is 1, 1 exclusive OR of 0 is 1, and that 1 exclusive OR of 1 is 0. So which denotes there was no error in the first block of data. So P1 doesn't have any error, so which is denoted with a logical 0. Next we'll go for the checking of your parity 2 with the correction bit of C2. We'll check the position of 2, 3, 6, 7. So 2, 3 are 0, 0, 6, 7 are 1, 1. So 0 exclusive OR of 0 exclusive OR of 0, 2, 3, and here we have it checks the positions of here, it checks the positions of here 2, 3, 6, 7. So now I received your data bits of 2 is position 2 is it is equal to 0, 3 is 0, 6, 7 are 0, 1. So now I replace that. So hence here 1 we obtain. So now 1 means there is an error is occurred. So hence C2 is replaced with logical 1. C3 can check the positions of 4, 5, 6, 7. Fourth position is received with 0, fifth position is received with 0, sixth position is received with 0, and seventh position is received with 1. So 0 exclusive OR of 0 is 0, 0 exclusive OR of 0 is 0, 0 exclusive OR of 1 is 1. So now just you counted number of ones received is odd. So we forwarded this message with the even parity. It is not satisfying with the parity 4. Hence, so there was an error is occurred while you're checking your parity 4. So which I denoted C3 is equal to 1. Now let me generate the error correcting word. So by just placing C3 in your most significant bit position and C1 is in your least significant bit position. C3 is placed at, and now it is 110 of 2, so which is decimal equivalent of 6, and now we have identified the where the position of error is occurred, and now we will flip that bit. Okay, with if I receive with the 0, I will flip that bit with a 1. If I receive with the 1, so I will flip that with a 0. So like that we can correct it as well as we can detect. So this is about our Hamming code technique of identifying your errors. The next class will start your Boolean algebra. Thank you.